In this video, we're going to begin our study of infinite series by looking at sequences. So, a sequence is represented in braces. A sub n is an ordered collection of numbers. A1, A2, so on and so forth, up through A sub n, which is defined by a function f on a set of sequential integers. So the values a sub n, or I should say a sub I, are the terms of the sequence. And I is called the index. And AI is given by a formula. We refer to the function f of I as the general term. Or the explicit formula. Of the sequence. Set of values, call them I, on which the sequence is defined. Is the domain of the sequence. Right, there could be times where a sequence is defined recursively or given by a recurrence relation. Right, so a sequence that is defined recursively or given by a recurrence relation is one in which one or more terms of the sequence are given explicitly, and subsequent terms are defined in terms of earlier terms in the sequence. Now, it's important to note that the index of a sequence need not start at 1. Right? The start of the sequence can be any integer value. So here we're going to look at a table for several sequences. Okay. So starting off, we have sequence whose general term is given by 1 minus 1 over n. The domain will be n greater than or equal to 1. Of course, understood that these are integers only. And the sequence would be 0, a half, 2/3, 3/4, 4/5, so on and so forth. Next sequence given by the general term Bn equals 364.5 n squared all over n squared minus 4. It has a domain of n greater than or equal to 3. And the sequence is 656.1, 486, 433.9, 410.1, 396, so on and so forth. Third sequence has general term cosine of n pi over 2. And our integers greater than or equal to 0. And the sequence is 1, 0, negative 1, 0, 1, 0, so on and so forth. And finally, we can look at the sequence that has general term d sub n equals -1 to the n times n. Domain has n greater than or equal to 0. Sequence is 0, -1, 2, -3, 4, so on and so forth. So another example. Let's suppose that you have a cake. Okay. So let's draw a circle. And so let's say that this represents our cake. Right? Now, today we eat half the cake. So let's say that looks to be about half. Oh, not quite. That looks better. And so just say that we'll shade this in to represent that we ate half the cake. Now, on the second day, we eat half of what remains. So let's say we do this. All right, so again, shade in what we ate. Third day, we eat half of what remains. Right? On the fourth day, we will eat half of what remains. Let me continue on in this pattern. The question is, we want to determine a sequence that represents the amount of cake that remains after each day. Right? So what we're going to do is say let n represent the day. So we're going to have n. Right, so we're going to have a table of n, the day, and remaining cake. So obviously, we're going to say the 0th day, we have the entire cake, right? Whole cake. First day, we ate half, so we have half remaining, right? Second day, we ate half of the half. So we now have a quarter remaining. Third day, we ate half of that quarter. So we have an eighth remaining. Fourth day, we ate half of the eighth. So we have a 16th remaining. And this can go on, so on and so forth. So the sequence of remaining cake would be a half, a quarter, an eighth, a 16th, so on and so forth. Or we can define this with a general term. Right, notice each denominator is a power of 2. Isn't this 1 over 2 to the n? All right, so it's a sequence given by 1 over 2 to the n such that n is greater than or equal to 1, and it's an integer. Not every sequence can be given by a function, right? So to see this, consider this sequence. All right, general term f of n. I'll give you a few seconds to see if you can figure out what this sequence is representing. Okay. So this sequence is the digits of pi. So particularly f of n represents the nth digit of pi. One of the most famous sequences is a recursively defined sequence. And it's this sequence right here. Right. This sequence is the Fibonacci sequence. So what the Fibonacci sequence does is it starts by defining the first two terms as 1. So f1 is 1, f2 is 1. Then define each subsequent term, fn. It's just the sum of the previous two terms. All right, obviously for n greater than or equal, greater than 2. So this is the recursive definition for the Fibonacci sequence. Now, it can be shown that the limit as n goes to infinity, fn over fn plus 1 is equal to 1 plus root 5 all over 2. We call that phi, and this is known as the golden ratio. Now, when we study sequences, our main interest is in the convergence of the sequence. So we say that the sequence given by an converges to a limit capital L, and we write that the limit as n goes to infinity of a sub n equals L, or a sub n converges to L if for every epsilon greater than 0, there is a number, capital N, such that the absolute value of a sub n minus L is less than epsilon for all little n greater than or equal to capital N. If no limit exists, we say that a sub n diverges. If the terms increase without bound, that is, they just keep on increasing, or the limit is infinite, we say that a sub n diverges to infinity. Now, what is this really saying? Right? So let's try and visualize it. Right, so here we have a coordinate system, and let's say this line right here is going to represent the value L. And now let's make this our limit, or our sequence. So there's one value of the sequence, there's another value of the sequence, here's a value, 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 right, so on and so forth. All right, let's connect these. Right? So let's now choose some epsilon. So we assume that some epsilon is given to us. That's close enough. Right, so above we'd have L plus epsilon, below we have L minus epsilon, right? This is known as the epsilon band. So there is a value, capital N, such that for every value larger than it, every term in the sequence falls within this epsilon band. Right? In this case, that N would be right here. Right? So for any term in the sequence to the right of this line would fall within this epsilon band. And there are two useful facts. First, the limit of the sequence does not change. If we change or drop finitely many terms, second, if C is some constant, and A sub n is equal to C for all n greater than or equal to some fixed value big N, then A sub n will converge to C. Right, so there's a proposition that states if the limit as x approaches infinity of f of x exists, then the sequence a sub n equals f of n converges to the same limit. I.e., right, so in other words, the limit as n approaches infinity of a sub n is equal to the limit as x approaches infinity of f of x. So what this proposition is saying is that we can evaluate the limit of a sequence the same way we would evaluate the limit of a function. Right, let's take a look at some limits. So we want the limit as n approaches infinity, 5 minus 3 over n squared. Well, we can write this as the limit as n approaches infinity of 5 minus the limit as n approaches infinity of 3 over n squared. Right, well, limit of 5 is 5. Limit of 3 over n squared is 0. So we get a limit of 5. What this means is that the sequence 5 minus 3 over n squared converges to the value of 5. So limit as n approaches infinity, 3n to the 4th minus 7n squared plus 5 all over 6 minus 4n to the 4th. Right, now we can look at this and we go, well, in the numerator, the dominant term is this n to the 4th, right? In the denominator, this dominant term is n to the 4th. So this behaves like this limit. And that limit is negative 3/4. So the sequence given by this converges to negative 3/4. What about 2 to the n over n squared? Well, to see that 2 to the n actually increases faster than n squared, we can use L'Hopital's rule. We get 2 to the n log 2 all over 2n. Right, we have to do L'Hopital's rule again. So 2 to the n times log squared of 2 all over 2. We can rewrite this as 2 to the n minus 1 log squared of 2. Well, that is clearly infinity. So what we say is that the sequence given by here diverges to infinity, or it's increasing without bound. Finally, let's take a look at the limit as n goes to infinity of 1 plus 4 over n all raised to the nth power. what we can do is rewrite this as e to the natural log of 1 plus 4 over n to the nth power. That is the limit as n approaches infinity, or I'm sorry, that is e raised to the limit as n approaches infinity of n times the natural log of 1 plus 4 over n. So we're going to take a look at that limit. Well, we can rewrite it. Natural log of 1 plus 4 over n all over n to the minus 1. Now we can use L'Hopital's rule. Negative 4 over n squared divided by 1 plus 4 over n all over negative n to the minus 2. Simplify this, and we get the limit of 4 over 1 plus 4 over n. This is going to give us 4 over 1, which is just 4. So what we see is that 1 plus 4 over n to the nth power converges to e to the 4th. We now examine a special type of sequence. A geometric sequence. Is a sequence of the form a sub n equals cr to the n, where both c and r are non-zero constants. R is called the common ratio. Right, let's look at convergence of the geometric sequence. If r is greater than 0, then look at the limit. We can factor out the c. Right? Now, if r is larger than 1, if r is less than 1, then the limit's 0. If r equals 1, the limit is c. And if r is larger than 1, the limit diverges to infinity. Right, so notice from this, we conclude that cr to the n converges for 0 less than r less than or equal to 1, and it diverges for r larger than 1. Now, what if r is less than 0? Well, then we know the absolute value of r would be larger than 0. Now, if r is less than negative 1, not less than, sorry. If r is larger than negative 1, then we know that the absolute value of r is going to be between 0 and 1. So if we take a look at the limit of the absolute value of cr to the n, That's the absolute value of c times the limit as n goes to infinity, absolute value of r to the n, which is 0. But what does it say about the limit of cr to the n? Well, consider a sequence a sub n such that the limit as n goes to infinity of the absolute value of a sub n is equal to 0. Now, note that negative absolute value of a sub n will be less than or equal to a sub n, which is going to be less than or equal to the absolute value of a sub n. Also, if we take a look at the limit, n goes to infinity, absolute value of a sub n, we know that's 0, which implies that the limit as n goes to infinity, negative absolute value of a sub n is also 0. And so by squeeze theorem, we can conclude that the limit as n approaches infinity of a sub n itself is 0. Using this, we can conclude that the limit as n goes to infinity of cr to the n is 0. Right, so notice this is a situation much like this. Remember, r is greater than negative 1. Right, so the sequence is doing something like this, right? Even though the values bounce back and forth between positive and negative 1, notice that the absolute value of the values are shrinking to 0. So the limit itself is 0. What if r is less than negative 1? Well, now let's first consider what happens if r is negative 1. Right, then our sequence, cr to the n, is going to bounce between negative c and positive c, right? Depending on the parity of n, right? So odd n gives us negative c, even n gives us positive c. Right, so that'll be this type of situation. Clearly that limit does not exist. Finally, if r is less than negative 1. Well, then the absolute value of r would be larger than 1. All right, so we have cr to the n bouncing back and forth between positive and negative values. Furthermore, limit as n approaches infinity of the absolute value cr to the n is going to equal absolute value of c limit of absolute value of r to the n, which is infinity, right? Because the absolute value of r is larger than 1. Right, so this is a case that would look something like this. Right? Yes, we're bouncing back and forth, But notice here that we're getting further and further away from 0. So this says this limit also does not exist. So what we can conclude here is that CR to the n converges for r greater than -1 and diverges for r less than or equal to -1. If we now combine these two results, the geometric sequence CR to the n converges only for -1 less than r less than or equal to +1. It'll diverge for any other value of r. So we say a sequence is increasing for all n larger than some number big N if a sub n is less than or equal to a sub n plus 1 for all such little n. We say the sequence is decreasing for all n larger than some value big N if a sub n is greater than or equal to a sub n plus 1 for all such values of little n. We say the sequence is monotonic or a monotone sequence for all n larger than some big N if it is either increasing or decreasing. One of the most important theorems from the study of sequences is called the monotone convergence theorem. And it says if sequence a sub n is a bounded monotonic sequence, then the sequence of a sub n converges. All right, so this gives us a way to determine whether a sequence converges. Now, a proof of this is given in a typical introductory course in real analysis. All right, so what we're going to do is going to show that this sequence converges. First, we're going to note that we can define this recursively as such. Define a sub 1 to be the square root of 2. And a sub n is equal to the square root of 2a sub n minus 1 for all n greater than 1. Now, note that square root of 2 is less than 2. Assume that a sub j is less than 2 for some j larger than 1. Then notice that a sub j plus 1, which is equal to the square root of 2 times a sub j, would be less than the square root of 2 times 2, which equals 2. Notice what this means. This means that a sub j plus 1 is also less than 2. Therefore, 2 is an upper bound. It is also clear that 0 is a lower bound. For a sub n. Right. So this proves that a sub n is bounded. Now note, square root of 2 is less than the square root of 2 times the square root of 2. Let's assume that a j minus 1 is less than a sub j for all j greater than or equal to 2. Let's just say larger than 2. Take a look at a sub j plus 1. Right, well, that is the square root of 2 times a sub j. But we know that is going to be larger than the square root of a sub j times a sub j, right? Which is itself a sub j, which implies that a sub j is less than a sub j plus 1. Therefore, a sub j is increasing for all j greater than 2, which means that the sequence a sub j is monotonic. What we have just shown is that a sequence is bounded and monotonic. Therefore, the sequence converges by the monotone convergence theorem. Of course, notice that this doesn't tell us what it converges to. Well, let the limit as n approaches infinity of a sub n be the limit L, right? On the other hand, the limit as n approaches infinity of a sub n would have to equal the limit as n approaches infinity of the square root of 2 times a sub n minus 1. Right? Well, that equals the square root of the limit which equals the square root of 2 times the limit. But that limit has to be L. Thus what we have is L has to equal the square root of 2L, which means L squared is equal to 2L, or L squared minus 2L is 0. Obviously this means that L times L minus 2 is 0, which implies that L itself is either 0 or 2. However, root 2 is a lower bound. Right? Because we just showed that it's monotonic increasing and it starts at root 2. So what we have is L cannot be 0. Therefore, we find that L must be 2, and so this sequence actually converges to 2. A sequence A sub n is bounded from above if there is a number, call it capital M, such that a sub n is less than or equal to big M for all values of little n. This number M is called an upper bound. Sequence is bounded from below if there is a number little m such that a sub n is greater than or equal to little m for all n. Right? And little m is called a lower bound. The sequence a sub n is called bounded if it is bounded from above and from below. A sequence that is not bounded is called unbounded. So let a sub n be a sequence that converges to some value L. What we know is that there has to exist some n larger than 0 such that the absolute value of a sub n minus L is less than epsilon for all epsilon greater than 0 and for all n greater than big N. What this means is that for n larger than capital N, L minus 1 is less than a sub n, which is less than L plus 1. Now, if capital M is any number larger than L, no, I'm sorry, larger than L plus 1, and also larger than the numbers A1, A2 through A sub little or A sub capital N, then we know that AN is going to be less than big M for all little n. Now, we know there exists such an M since L must be finite. And each of the A1, A2 through A sub n must also be finite. What this means is that M is an upper bound. Right, for our sequence. Similarly, we can find a number little m, right, such that a sub n is larger than little m for all n, which obviously means that little m is a lower bound for our sequence. Notice what this means. This means that our sequence is bounded, right? It's both bounded from above and below. So this is stated formally. And it says if the sequence A sub n converges, then A sub n is bounded. Another way of writing this, and it's a more useful way, is if the sequence A sub n is not bounded, then the sequence A sub n does not converge